Speaking, probability is the science of chance behavior. And I just want to start with an example taken from the course textbook on page 103. You will see a data set that has been provided by Stats Canada, and it shows that in 2012, nearly 214,000 Canadians were granted a degree. Okay, so it shows in the table the type of degree and also the number of males and the number of females, and then the grand totals. So let's suppose an employer was interested in knowing that if they were to randomly select a person from this graduate pool, what would be the probability that the person would be female? How would you answer that? Well, you would take the proportion of females. And so you would look and go, well, the total number of females in the data set is 127,326. And then you would divide that by 213,708, which is the total number of people in the study. And that is generally what we do to find the probability. It's the number of ways divided by the total number of ways, where here we're looking for the total number of females divided by the total number of people, which gives us then the proportion, which is also the probability. Okay, so we're going to go and look at now the methods of assigning probabilities. There's three types: the classical method, the relative frequency method, and then finally the subjective probability, which is also called personal probability. The first one here is classical probability. And so we use the laws of mathematics or physics to come up with those probabilities before you even actually have the event. So suppose we have a coin and it's been determined to be a fair coin through physics and the weights. We know that the coin has been made perfect and it's weighted so that each side is equally likely to occur if you were to flip the coin. And so it's determined a priori before performing the experiment. Okay, and a simple experiment is just tossing a coin. Okay, so we have here the capital P, that's our notation, that stands for probability, and the capital E is the event. So you define the event E as being tossing a coin or rolling a dice, and it's equal to the number of possible outcomes, and then divided that by capital N, which is the total number of possible outcomes. Okay, and also probability is a number between 0 and 1. If you were to calculate a probability and it comes out less than 0 or greater than 1, then you've done something wrong and you need to find out where that mistake was. So it must be a number between 0 and 1. Okay. 2, the relative frequency probability. This is based on historical data or empirical data, and it's not on rules or laws. What happens is we repeat the experiment many times to determine what the probability is, or the long run frequency. So let's take our coin again. So we flip the coin several times and we find out that the coin isn't weighted perfectly and it's not quite a fair coin. You might find that the number of heads and tails is 0.48 and 0.52, right, instead of 50-50. So that is going to be the relative frequency. It needs to be repeated several times to get a good idea. And the more it's repeated, the closer you get to the actual truth of the real probability. So it's the number of ways, right here, the number of ways in the numerator that the event occurred divided by the total number of opportunities for the event to occur. Okay. And the third one, last one, is the subjective probability. It's also a personal probability. So all of us have done this from time to time. We are, let's say, on our way to work, and you're trying to get there, and you go, well, what's the chances of getting to work on time? And you might think maybe it's 80%, and then you get into heavy traffic, and then you revise your probability and you revise and go, well, the chances now of getting to work on time is maybe 60%. So that is subjective probability, and it's based on an individual's degree or belief. Okay, and there's some examples there. All right, so the structure of probability, starting with experiment, we need to define some of these structure of probability. So experiment is a process that produces an outcome, okay? And so even tossing a coin, rolling a dice, all of those produce an outcome. They are all considered experiments. A trial is one repetition of that process. Okay, so if you were to repeat flipping a coin several times, let's say 10 times, that would be equal to 10 trials. An elementary event cannot be decomposed or broken down into other events, and an event itself is an outcome of an experiment. It may be an elementary event, or it may be an aggregate of elementary events. Here is some notation, A and E. Those could be events. You could also have X or Y or B, anything of those types. Then they can be, then we would assign, let's say, the probability of X, where X is the event. Okay, and here's 5 examples showing what an experiment is. All 5 of these are showing a process that produces an outcome. So any process that produces an outcome is defined as an experiment. Now there's many ways to display a sample space, and the sample space are all those outcomes. So let's suppose we have an experiment, and we randomly select, without replacement, 2 families from the residents of Tiny Town, and there's 4 different families in the town, and so each ordered pair in the sample is an elementary event, right? And so it gives an example, and here is our sample space right here, the listing. So a sample space can be provided as a list or a roster, and it shows all of the possible outcomes. Okay, and so we have 4 families, and so the first family would be chosen. Let's say it's family A. Then the second family is chosen, and let's say it's family B. Then AB is one outcome. So even though it's done in 2 stages, it's still one outcome. And then you might be interested in getting some data from those families. Are there children in the household, or the number of automobiles, and so forth. Okay, another way to show a sample space is using set notation. You can define S here as equal to X and Y, where X is the family selected on the first draw and Y is the family selected on the second draw. Okay, so it's just another way to display the sample space. Okay, another one is a tree diagram, which is a sequential description of the sample space. And you can see here in stage 1, this is done in stages. So stage 1, there are 4 choices. Okay, and stage 2, once you have made a choice on stage 1, you have to stay with that choice. And then stage 2, there are 3 choices. And so if we take the number 4 and multiply it by 3, let me get that in there. Whoops, I can't get the words choices, but you know what I mean there. That's 4 choices and 3 choices. And if we take the number of choices at stage 1, 4, and multiply that by 3, we get a total of 12 outcomes. So there are 12 outcomes with this experiment showing 4 families where we select 2 families without replacement. So just another way to display the sample space. Moving on to sets. So we have some set theory here. So let's suppose we have A, and it's been described as being the set as 1, 3, 4. And let's suppose we have B is described as 2, 3, and 5. Then what would be the union of A and B? The union in this case would be everything that is in A and everything is in B. So you want to think of union as being defined as or. You can use the word or to describe the union. So A or B or both. And so A union B would be 1, 2, 3, 4, and 5. Moving on to the intersection. The intersection. So let's define A at this time as being 1, 9, and 10, and define B, right? These are events B, event A and event B, and let's say event B has the elements 2, 3, and 9. Okay, so this time, what is the A intersection of B? You can think of intersection as the word and. So the overlap, what do they both have in common? And so in this case, A and B both have the number 9 in common. So A intersect B, or A and B, would be the set 9. Okay, mutually exclusive. Let's say we have two events. We have an A and we have a B, and you can see there's no overlap. And so that would be, you would go, well, A can occur, the event A can occur, or the event B can occur, but not both. Okay, we'll look at that when we attach the probabilities to it. An independent event is an occurrence of one event does not affect the occurrence or non-occurrence of the other events. So if I was to say roll a dice or toss a dice and I get a 3, then that 3 will not affect any future tosses. So if I toss it again, I got another 3. So each toss is going to be independent of each other. So I could get 5 3s in a row. That does not mean that the next one won't be a 3. It very well could be a 3. Okay, so that's independent events. The events are not influenced by what has already happened in the past. Okay, and we're looking now, collectively exhaustive events. Collectively exhaustive events contains all elementary events for an experiment. They are mutually exclusive, meaning there's no overlap, and collectively exhaustive means it's complete. So nothing has been left out. So all of the outcomes have been taken into consideration. And complementary events, a complementary event, so suppose we have the dice and we define event A. Let's say A is the event that I toss the dice and I get an even number, so 2, 4, or 6. Then a complement would be the event that I toss the dice and I get an uneven number, so 1, 3, or 5. Okay,